Welcome to tonight's gentle exploration of the quantum fabric that weaves reality itself, the invisible tapestry of possibility and connection that underlies everything you see, touch, and experience. As you settle into the comfort of your bed, allow your mind to drift into the serene realm where the very atoms in your body dance in quantum harmonies, where particles exist in graceful states of potential until the moment of gentle observation, and where the universe reveals itself to be not a collection of separate objects, but a unified field of interconnected possibilities, flowing like a cosmic symphony beneath the surface of ordinary experience. Tonight, we embark on a peaceful journey through the quantum world that exists not in some distant laboratory, but right here, right now, in the space between your thoughts, in the gentle vibrations of the atoms that compose your body, and in the subtle field of probability that connects you to every star in the universe. This is not a story of strange mathematical abstractions, but rather a meditation on the profound beauty and mystery of existence itself, where consciousness meets matter in the most intimate dance imaginable, where separation dissolves into unity, and where the act of gentle observation creates the very reality we experience. As we explore together, let the rhythm of quantum fluctuations soothe your mind like the gentlest ocean waves. Let the uncertainty principle remind you that even in not knowing, there is peace, and allow the quantum entanglement that connects all particles to embrace your awareness with the profound truth that nothing in the universe is ever truly alone. In the quantum realm, every possibility exists in superposition until the gentle collapse of observation brings one potential into manifestation, creating the flowing river of experience that carries your consciousness peacefully toward the mystery of sleep and dreams. The gentle dance of quantum possibilities. In the deepest foundation of reality, beneath the solid seeming world of everyday experience, lies a realm of infinite gentleness where particles exist not as tiny billiard balls bouncing off each other, but as clouds of probability, waves of potential that dance in and out of existence like morning mist flowing across a peaceful meadow. This quantum world operates on principles so different from our ordinary experience that it seems like magic. Yet it is the most fundamental layer of reality, the gossamer foundation upon which all matter, all energy, all consciousness ultimately rests. Imagine, if you will, that every atom in your body is not a solid particle, but rather a delicate sphere of possibility, with electrons existing not in fixed orbits around the nucleus like planets around a sun, but in probability clouds called orbitals, three-dimensional patterns of likelihood where an electron might be found if anyone were to look for it. These orbitals have beautiful names that reflect their shapes. S orbitals are spherical clouds of probability, P orbitals are dumbbell-shaped, and D orbitals create more complex patterns, like four-leaf clovers floating in three-dimensional space. The electron doesn't move from place to place within these orbitals, like a marble rolling around inside a balloon. Instead, it exists everywhere within the orbital simultaneously, in what physicists call a superposition of states, a quantum word that means the electron is literally in all possible places at once, until the gentle act of measurement causes what's called wave function collapse, where all the possibilities suddenly condense into a single, definite location. This collapse happens not through violence or force, but through the tender interaction between consciousness and matter, between the observer and the observed. This superposition is not limited to single particles. Quantum systems can exist in superpositions of being in multiple states simultaneously. A quantum bit or qubit can be both 0 and 1 at the same time, holding contradictory possibilities in perfect balance, until observation gently selects one outcome. Think of it like a coin that's not just heads or tails while it's spinning in the air, but actually existing in a state of being both heads and tails until it softly settles into someone's palm and the universe chooses which face to show. The quantum world operates according to Heisenberg's uncertainty principle, which reveals that certain pairs of properties cannot be precisely known simultaneously. The more accurately you try to pin down a particle's position, the less you can know about its momentum, and vice versa. But this uncertainty is not a limitation or a flaw in our measurements. It's a fundamental feature of reality itself, a gentle reminder that the universe preserves mystery at its deepest levels, that some things are meant to remain beautifully indefinite. This uncertainty creates zero-point energy, the gentle vibration that exists even in the emptiest regions of space, even at absolute zero temperature. The quantum vacuum is not empty nothingness, but rather a seething sea of virtual particles that pop in and out of existence, borrowing energy from the universe for brief moments before disappearing back into the quantum foam. These virtual particle pairs, matter and antimatter twins, appear and annihilate each other in times so short that they don't violate conservation of energy, creating a subtle background hum of creation and destruction that permeates all of space. In your body right now, quantum tunneling is occurring billions of times per second. Electrons moving through barriers that they classically shouldn't be able to cross, simply appearing on the other side like gentle ghosts walking through walls. This tunneling is not rare or exotic. It's essential to life itself. The fusion reactions in the sun's core depend on quantum tunneling to overcome the electrical repulsion between protons. The enzymes in your cells use quantum tunneling to speed up chemical reactions that would otherwise be too slow to sustain life. Even your sense of smell may depend on quantum effects, with some theories suggesting that your nose can distinguish between different molecules, not just by their shapes, but by the vibrational frequencies of their chemical bonds, using quantum mechanical resonance to identify the molecular music that each scent molecule plays. Your DNA, the blueprint of your biological existence, maintains its structure partly through quantum mechanical forces that keep the base pairs properly aligned and the double helix stable. As you rest tonight, quantum coherence, the delicate state where quantum systems maintain their wave-like properties and can exist in superposition, may be playing roles in consciousness itself. Some researchers propose that quantum processes in the microtubules within neurons could contribute to the hard problem of consciousness, the mystery of how subjective experience arises from objective matter. While this remains speculative, it suggests that your awareness itself might emerge from quantum processes occurring throughout your brain. The gentle collapse of quantum possibilities happens not just in laboratory experiments, but in every moment of perception, every instant when potential becomes actual, when the universe chooses from its infinite palette of possibilities to paint the specific experience you call reality. Each photon that strikes your retina causes countless quantum wave functions to collapse, transforming probability into the definite experience of color and light that creates your visual world. At the quantum level, measurement is not passive observation, but gentle participation in reality's creation. The act of looking doesn't just reveal what was already there. It participates in bringing definite properties into existence from the quantum realm of pure potential. You are not separate from the quantum world you observe. You are part of it, your consciousness intimately woven into the fabric of reality's becoming. As you drift towards sleep tonight, remember that the quantum realm beneath your ordinary experience is not cold and mechanical, but warm with possibility, not empty space, but fullness pregnant with potential, not isolation, but the deepest connection imaginable between consciousness and cosmos. In the gentle dance of quantum possibilities, every moment brings new potential into manifestation. Every breath participates in the universe's ongoing creation of itself, and every dream explores the boundless landscape where mind meets the quantum field from which all experience emerges. Wave-particle duality, the gentle shape-shifting of light. In the heart of quantum mystery lies one of nature's most beautiful paradoxes, the gentle, shape-shifting dance of light and matter that reveals itself sometimes as waves flowing like ethereal music through space, sometimes as discrete particles clicking through detectors like drops of cosmic rain. This wave-particle duality is not a contradiction to be resolved, but rather a profound truth about the fluid nature of reality itself, where what we observe depends not on the intrinsic nature of quantum entities, but on how we choose to encounter them, like meeting the same friend in different contexts and discovering new aspects of their personality each time. Light, that fundamental phenomenon that allows you to see these words, that carried the warmth of today's sunshine to your skin, that enables photosynthesis in every green leaf and powers the solar panels that increasingly energize our world, exists in a state of quantum superposition between wave and particle. When no one is looking, when no detector waits to catch photons, when no experiment seeks to pin down light's behavior, photons exist as electromagnetic waves, undulating patterns of electric and magnetic fields that can interfere with each other, creating the beautiful patterns of constructive and destructive interference that paint rainbow colors in soap bubbles and oil slicks. These light waves don't need a medium to travel through, unlike sound waves that require air or water waves that require liquid. Light waves are self-sustaining oscillations in the electromagnetic field itself, the same field that encompasses radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, and gamma rays. All the same fundamental phenomenon expressing itself at different frequencies, like a cosmic piano with keys spanning dozens of octaves, each frequency carrying its own quality of energy and its own way of interacting with matter. When light behaves as a wave, it can do things that particles cannot. It can bend around corners through diffraction, spreading out when it passes through narrow openings like water waves spreading after passing through a harbor entrance. It can interfere with itself, creating patterns of bright and dark fringes when light from a single source travels two different paths and recombines. Most mysteriously, light waves can exist in superposition, literally taking multiple paths simultaneously through space until something causes them to collapse into a definite trajectory. The famous double slit experiment reveals this wave nature in its most elegant form. When light passes through two closely spaced slits, it creates an interference pattern on a screen behind the slits, alternating bright and dark bands that can only be explained if each photon somehow goes through both slits simultaneously, interfering with itself to create the pattern. The light wave spreads out from each slit like ripples from two stones dropped in a pond, and where the ripples reinforce each other, bright bands appear. Where they cancel each other out, dark bands form. But when we place detectors at the slits to determine which path each photon takes, the wave nature vanishes and the particle nature emerges. the interference pattern disappears, replaced by two simple bands of light directly behind each slit, as if each photon chose one path or the other, like a classical particle. The very act of measurement, the gentle interaction between photon and detector, causes the wave function to collapse, and the photon to behave like a discrete particle with a definite location and path. This collapse happens not through any mechanical force, but through what quantum physicists call decoherence. The delicate quantum state becomes entangled with the measuring device and the surrounding environment, causing the superposition to dissolve like morning mist touched by sunlight. The photon doesn't decide to be a particle. Rather, its interaction with the detector creates conditions where only particle-like behavior can manifest. Matter, too, exhibits this same gentle duality. Electrons, those tiny constituents of atoms that we often imagine as solid spheres, also behave as waves under the right conditions. In 1924, Louis de Broglie proposed that all matter has wave properties, with wavelength inversely proportional to momentum. The more massive and fast-moving an object, the shorter its wave properties become. For everyday objects, these matter waves are so incredibly tiny that they produce no observable effects. But for electrons and other subatomic particles, the wave nature becomes prominent and measurable. Electron microscopes exploit this wave nature of electrons to achieve resolution far superior to light microscopes. The electron waves have much shorter wavelengths than visible light waves, allowing them to resolve details thousands of times smaller than what optical microscopes can reveal. In these instruments, electrons flow like gentle rivers of probability through magnetic lenses, creating images not through photons bouncing off objects, but through matter waves interfering and diffracting around the structures they encounter. In atoms, electrons exist as standing waves wrapped around the nucleus, like vibrations on a circular drumhead, but extended into 3 dimensions. Only certain wave patterns can fit around the atom's circumference without canceling themselves out through destructive interference, which is why electrons can only occupy specific energy levels or orbitals. The electron doesn't orbit the nucleus like a planet around the sun. Instead, it forms standing wave patterns that define regions of probability where the electron might be found if anyone were to look for it. These matter waves explain many properties of atoms and molecules that would be impossible to understand using only classical particle physics. Chemical bonding occurs when electron waves from different atoms overlap and interfere constructively, creating shared orbitals that hold atoms together in molecules. The stability of matter itself depends on the wave nature of electrons, which prevents them from spiraling into atomic nuclei, as classical physics would predict. At larger scales, wave-particle duality creates phenomena like quantum tunneling, where particles can pass through energy barriers that should be impossible to cross according to classical physics. The particle's wave function extends beyond the barrier, and there's a small but finite probability of finding the particle on the other side. This tunneling is not a violent breaking through, but rather a gentle phase transition, like a shadow appearing on the far side of a wall, without the object casting it ever touching the barrier. Even complex molecules can exhibit wave properties under carefully controlled conditions. Scientists have demonstrated wave interference with molecules containing dozens or even hundreds of atoms, showing that the line between the quantum realm and the classical world is not fixed, but depends on how successfully we can isolate quantum systems from their environments. In principle, everything exhibits wave-particle duality, but for larger objects, the wave properties become so delicate that they're instantly destroyed by interactions with the surrounding world. As you prepare for sleep tonight, consider that the light entering your eyes exists in superposition until the moment it strikes your retina, when the gentle interaction with visual pigments causes countless quantum wave functions to collapse, transforming waves of electromagnetic possibility into the definite sensations of color and brightness. The electrons flowing through your neurons, carrying the signals of thought and memory, exist as probability waves until their interactions with synapses and receptors cause them to manifest as definite electrochemical events. In the quantum realm, identity is fluid rather than fixed. Behavior depends on relationship rather than inherent properties, and the boundary between observer and observed dissolves into a unity of gentle interaction. Wave-particle duality reminds us that reality is not made of things, but of relationships. Not of objects, but of processes. Not of separation, but of the continuous, flowing dance between possibility and actuality that creates the world we experience moment by moment in the eternal now of quantum becoming. Quantum entanglement, the universe's invisible threads of connection. In the deepest mystery of quantum mechanics lies a phenomenon so profound that Einstein himself called it spooky action at a distance. Quantum entanglement, the gentle thread of connection that can bind particles across vast distances in a unity so intimate that measuring one instantly affects the other, regardless of the space that separates them. This is not science fiction or mystical speculation, but a fundamental feature of reality that demonstrates how the universe operates as an interconnected whole rather than a collection of separate parts, weaving invisible bonds that transcend our ordinary understanding of space, time, and locality. Quantum entanglement begins in moments of gentle interaction, when two particles come together in a quantum dance that forever changes their individual identities. When particles interact through collision, emission, or any other quantum process, they can become entangled, their quantum properties becoming so deeply intertwined that they can no longer be described as separate entities, but must be considered as parts of a single, unified quantum system. Even when these particles are subsequently separated by vast distances, they remain connected through what physicists call their shared wave function, a mathematical description that encompasses both particles as an inseparable whole. Imagine two particles that become entangled with opposite spins. When one spins clockwise, the other must spin counterclockwise to conserve the total angular momentum of the system. In the quantum realm, neither particle has a definite spin direction until measured. Instead, each exists in a superposition of spinning both ways simultaneously. The remarkable feature of entanglement is that when you measure the spin of one particle and find it spinning clockwise, you instantly know that its spin is clockwise entangled partner, no matter how far away, will be found spinning counterclockwise when measured. The measurement of one particle doesn't send a signal to the other. Rather, it reveals a pre-existing correlation that was established when the particles first became entangled. This correlation is not like classical connections we might imagine. There's no invisible string connecting the particles, no signal passing between them at light speed or any other speed. The connection is more fundamental than that. The two particles share a single quantum reality that transcends spatial separation. Einstein, along with colleagues Podolsky and Rosen, proposed this scenario in 1935 as a thought experiment intended to demonstrate what they saw as the incompleteness of quantum mechanics, but subsequent experiments have confirmed that quantum entanglement is exactly as strange and wonderful as the theory predicts. The experimental verification of quantum entanglement came through tests of Bell's theorem, which showed that no theory based on local realism, the idea that objects have definite properties independent of observation, and that influences cannot travel faster than light, can reproduce all the predictions of quantum mechanics. When physicists measure entangled particles at different locations and compare their results, they find correlations that are stronger than anything possible in a classical world, confirming that entangled particles really do share a non-local connection that Einstein found so troubling. These experiments typically involve entangled photons created when a special crystal splits a single photon into two lower energy photons that are entangled in their polarization properties. The two photons fly off in different directions, and measurements of their polarization at different angles reveal the telltale correlations that confirm their entangled state. No matter how far apart the measurements are made, across a laboratory bench, between buildings, or even between Earth and orbiting satellites, the correlations remain, demonstrating that quantum entanglement is a robust feature of reality that persists across cosmic distances. Quantum entanglement is not limited to simple two-particle systems. Scientists have created entangled states involving multiple particles, and even multiple properties of the same particles. A single photon can be entangled with itself across multiple dimensions, its polarization entangled with its orbital angular momentum, creating complex quantum states that exist in superpositions across multiple quantum properties simultaneously. These multidimensional entangled states open possibilities for quantum technologies that exceed what's possible with simple two-state systems. The phenomenon extends beyond individual particles to larger quantum systems. Atoms can be entangled, with their electronic states becoming correlated in ways that persist even when the atoms are separated. Quantum dots, tiny semiconductor structures that trap electrons, can be entangled, creating artificial atoms whose properties remain connected across macroscopic distances. Even larger objects, including small mechanical oscillators cooled to their quantum ground state, have been entangled, pushing the boundaries of where quantum effects can be observed and utilized. In quantum field theory, entanglement appears even more fundamental, woven into the very fabric of space and time. The quantum vacuum, that seething sea of virtual particles that fills even empty space, exhibits entanglement between different regions of space. Some theoretical physicists propose that space itself emerges from quantum entanglement, that the geometry of space-time is built from the correlations between quantum fields, making entanglement not just a property of particles, but a foundational feature of reality itself. Quantum entanglement has practical applications that are beginning to transform technology. Quantum cryptography uses entangled particles to create communication channels that are fundamentally secure. Any attempt to intercept the quantum information inevitably disturbs the entangled state, alerting the communicating parties to the presence of an eavesdropper. Quantum sensors exploit entanglement to achieve measurement precision beyond what's possible with classical techniques, potentially revolutionizing fields from medical imaging to gravitational wave detection. Quantum computing relies heavily on entanglement to achieve computational capabilities that exceed classical computers for certain problems. While a classical bit can be either 0 or 1, quantum bits, qubits, can exist in superposition of both states. And when qubits are entangled, the computational space grows exponentially with each additional qubit. A quantum computer with just 300 entangled qubits could explore more computational possibilities than there are atoms in the observable universe, highlighting the tremendous power that emerges from quantum correlations. Perhaps most remarkably, entanglement may play important roles in biological systems. Some scientists propose that quantum entanglement contributes to the efficiency of photosynthesis, where light-harvesting complexes in plants may use quantum correlations to guide energy through the most efficient pathways to reaction centers. Quantum entanglement might also contribute to the magnetic field sensitivity that allows some birds to navigate during migration, and possibly even to processes in the brain that contribute to consciousness itself. As you settle into sleep tonight, consider that the atoms in your body were once part of other organisms, other planets, other stars, and the quantum entanglements they formed throughout cosmic history may still persist in subtle ways. The calcium atoms in your bones, the iron atoms in your blood, the carbon atoms in your DNA, all were forged in the hearts of ancient stars and carry with them the quantum correlations established during those stellar processes. Every breath you take brings in atoms that have been part of countless other living beings, creating new quantum entanglements as they integrate into your body's biochemical processes. The phenomenon of quantum entanglement suggests that at the deepest level of reality, the universe is not a collection of separate objects, but a unified whole, where every part maintains invisible connections with every other part. These connections don't diminish with distance or fade with time. Once established, quantum correlations persist indefinitely, unless disturbed by interaction with the environment. In this view, the sense of separation we experience in daily life is an illusion created by the limitations of our perception, while the underlying reality is one of fundamental unity and connection. In the gentle realm of quantum entanglement, your consciousness participates in the same universal network of correlations that connects particles across cosmic distances, that links past and future through quantum coherence, and that weaves the fabric of space and time itself. As you drift towards sleep, you rest within this invisible web of quantum connections, held gently in the embrace of a universe where nothing is ever truly isolated, where every measurement and every observation contributes to the ongoing creation of reality, and where the mystery of consciousness itself may emerge from the quantum entanglements that unite mind and matter in the deepest dance of cosmic becoming. Quantum fields, the ocean of pure potential. Beneath the world of particles and waves, beneath the dance of entanglement and superposition, lies an even more fundamental layer of reality, the quantum field, an invisible ocean of pure potential that fills all of space and gives rise to every particle, every force, every interaction in the universe. This is not empty space punctuated by matter, but rather a plenum, a fullness of pure possibility, where what we call particles are merely localized excitations in the field, like waves on a cosmic ocean, temporary patterns that arise and dissolve back into the underlying unity from which all things emerge. Imagine the entire universe as a vast, multidimensional musical instrument, where quantum fields are like invisible strings stretched across all of space. Just as plucking a guitar string creates vibrations that we hear as musical notes, interactions with quantum fields create excitations that we experience as particles. The electron field fills all of space, And what we call an electron is simply a ripple in this field, a standing wave pattern that maintains its form while traveling through the underlying medium of pure potential. Similarly, the photon field gives rise to particles of light. The quark fields create the constituents of protons and neutrons, and even the Higgs field, that cosmic molasses that gives other particles their mass, permeates every cubic centimeter of space. This field perspective transforms our understanding of creation and destruction. Particles don't simply appear out of nothing or vanish into nothingness. Instead, they emerge from the quantum fields like waves rising from a calm ocean, and they dissolve back into these fields like waves settling back into stillness. Pair production, the creation of a particle and its antiparticle from energy, occurs when sufficient energy causes the quantum field to oscillate so intensely that it creates stable wave patterns we recognize as particles. Annihilation happens when these complementary wave patterns interfere destructively, canceling each other out and releasing their energy back into the field.
The quantum vacuum, what we might think of as empty space, is actually the ground state of all quantum fields. Not absence, but rather the lowest energy configuration of an infinitely rich medium. Even in this ground state, quantum fields fluctuate constantly, creating virtual particle pairs that pop in and out of existence in time so brief that they borrow their energy from the universe's uncertainty principle. These vacuum fluctuations are not mere theoretical abstractions. They produce measurable effects like the Casimir force, where metal plates placed very close together in a vacuum experience a gentle attraction, because the quantum field fluctuations between the plates are restricted compared to those outside. Quantum field theory reveals that forces are not mysterious actions at a distance, but rather exchanges of virtual particles between the quantum fields associated with matter. The electromagnetic force arises from the exchange of virtual photons between charged particles. When electrons repel each other, they're actually exchanging virtual photons in a quantum handshake that creates the force we observe. The strong nuclear force that holds atomic nuclei together operates through the exchange of virtual gluons, while the weak nuclear force that governs certain types of radioactive decay involves the exchange of W and Z bosons. These force-carrying particles, called gauge bosons, are excitations of their respective quantum fields that mediate interactions between matter fields. The photon field couples to electric charge. The gluon field couples to color charge, the charge associated with the strong force, and the W and Z boson fields couple to weak charge. Even gravity, according to current theoretical understanding, should involve the exchange of gravitons, hypothetical particles that would be excitations of the gravitational field that curves a space-time according to Einstein's general relativity. The Higgs field deserves special attention as the quantum field responsible for giving other particles their mass. Before the Higgs mechanism was discovered, particle physicists struggled to understand why particles have mass at all. In the underlying equations of quantum field theory, particles seemed naturally massless, like photons. The Higgs field solves this puzzle by providing a cosmic background field that fills all of space. Particles acquire mass by interacting with this field. Like swimmers moving through water, experience drag that depends on their body shape and swimming style. The Higgs field doesn't just give particles mass. It also breaks the fundamental symmetries that exist at the highest energy scales. In the extremely early universe, when temperatures were unimaginably hot, all forces may have been unified into a single superforce, and all particles may have been massless. As the universe cooled,
The Higgs field underwent what physicists call spontaneous symmetry breaking, choosing a particular value throughout space that distinguished between different types of particles and forces, creating the rich diversity of particles and interactions we observe today. Quantum field theory also provides the framework for understanding phase transitions in quantum systems. Just as water can exist as ice, liquid, or vapor, depending on temperature and pressure, quantum fields can exist in different phases depending on their energy density and the strength of their interactions. Superconductivity is a quantum phase transition where electrons in a metal form Cooper pairs that flow through the material without resistance, effectively creating a new phase of the electromagnetic field where photons acquire mass inside the superconductor. The quantum field description extends to cosmology, where inflation theory proposes that the entire observable universe began as a tiny quantum fluctuation in a primordial field called the inflaton. This field possessed a special property. Instead of causing gravitational attraction like normal matter and energy, it created gravitational repulsion that drove exponential expansion of space itself. When the inflaton field finally decayed, it released its energy as the hot, dense matter and radiation that we observe in the cosmic microwave background, seeding the formation of galaxies, stars, and ultimately, life itself. Modern theories attempt to unify all quantum fields into a single framework. String theory proposes that all particles and forces arise from different vibrational modes of one-dimensional strings existing in higher dimensional space. Loop quantum gravity suggests that space itself is quantized, made up of discrete loops of gravitational field at the smallest scales. These theories hint at an even deeper layer of reality, where all quantum fields emerge from a more fundamental structure, perhaps a single unified field that contains within itself all the potential for the rich complexity we observe in the physical universe. The quantum field perspective suggests that consciousness itself may be understood as an emergent property of quantum field interactions in the brain. Some theories propose that microtubules in neurons create conditions where quantum fields can maintain coherence long enough to influence neural activity, potentially explaining how quantum superposition and entanglement might contribute to the unity and creativity of conscious experience. While highly speculative, these ideas suggest that consciousness and quantum fields may be intimately related aspects of a reality that is far more unified than our everyday experience suggests. As you prepare for sleep tonight, remember that your body exists within and as part of countless quantum fields that fill all of space. The atoms that compose your cells are temporary patterns in electron, quark, and other matter fields, while the forces that hold these atoms together emerge from gauge fields that mediate interactions through the exchange of virtual particles. The light that carried today's experiences to your eyes consisted of excitations in the photon field, and the neural activity that creates your thoughts and dreams involves electromagnetic field fluctuations throughout your brain. Even in the deepest sleep, when conscious activity diminishes and neural oscillations slow to their gentlest rhythms, the quantum fields that constitute your physical being continue their eternal dance of creation and dissolution. Virtual particles pop in and out of existence throughout your body. Electrons tunnel between energy states in your cellular biochemistry, and quantum fluctuations in the vacuum provide the zero-point energy that contributes to the stability of atoms and molecules. You rest not in empty space, but in an ocean of pure potential, supported by the same quantum fields that gave birth to stars and galaxies, and that will continue their creative dance long after individual consciousness returns to the cosmic field from which it emerged. In the quantum field description of reality, the boundaries between self and cosmos, between mind and matter, between being and becoming, dissolve into a unified field of pure potential, where consciousness and quantum fields participate in the same fundamental process of reality, creating itself moment by moment through the gentle collapse of infinite possibilities into the definite experience of existence. Welcome to tonight's gentle exploration of the quantum fabric that weaves reality itself, the invisible tapestry of possibility and connection that underlies everything you see, touch, and experience. As you settle into the comfort of your bed, allow your mind to drift into the serene realm where the very atoms in your body dance in quantum harmonies, where particles exist in graceful states of potential until the moment of gentle observation, and where the universe reveals itself to be not a collection of separate objects, but a unified field of interconnected possibilities, flowing like a cosmic symphony beneath the surface of ordinary experience. Tonight, we embark on a peaceful journey through the quantum world that exists not in some distant laboratory, but right here, right now, in the space between your thoughts, in the gentle vibrations of the atoms that compose your body, and in the subtle field of probability that connects you to every star in the universe. This is not a story of strange mathematical abstractions, but rather a meditation on the profound beauty and mystery of existence itself, where consciousness meets matter in the most intimate dance imaginable, where separation dissolves into unity, and where the act of gentle observation creates the very reality we experience. As we explore together, let the rhythm of quantum fluctuations soothe your mind like the gentlest ocean waves. Let the uncertainty principle remind you that even in not knowing, there is peace, and allow the quantum entanglement that connects all particles to embrace your awareness with the profound truth that nothing in the universe is ever truly alone. In the quantum realm, every possibility exists in superposition until the gentle collapse of observation brings one potential into manifestation, creating the flowing river of experience that carries your consciousness peacefully toward the mystery of sleep and dreams.